Hey everyone, and welcome to this explainer. I'm the lead developer for the vision systems on the TiCare project. Today, we're really going to look under the hood. I'm walking you through a complete engineering case study on how my team and I successfully bridge the gap between cutting-edge deep learning and actual physical robotics in the real world. So if you've ever wondered what it literally takes to make machines see and then act on that vision in real time, well, you are absolutely in the right place.
Look, I want to start by framing our ultimate objective here. Imagine speaking to a robot and it autonomously finds and guides you to your lost glasses. Sounds kind of like science fiction, right? But this is exactly the end user impact we set out to build. Because before we get bogged down in the deep technical complexities of ROS nodes or neural network weights or data distribution services, we really have to remember the goal. We're creating a seamless, intuitive human-robot interaction. And as you know, making something look this simple to an end user requires an incredibly complex backend.
Okay, let's dive right into the structure of how we tackle this. First, we'll cover the autonomous guide goal. Second, data and vision training. Third, our custom ROS2 deployment. And finally, seamless system integration. Jumping right into part 1, the autonomous guide goal.
Our target hardware for this was the PAL Robotics TIAGo. Now, if you're in the robotics industry, you definitely know the TIAGo. It's a seriously robust, versatile mobile manipulator. It's got a native navigation stack, a multi-degree of freedom arm, and crucially for my part of the project, an RGB camera mounted right in its head. We were tasked with programming this complex piece of machinery to serve as our autonomous guide. And honestly, this wasn't just some software simulation. We were dealing with physical payloads, battery constraints, real-world lighting, the whole shebang. Fun fact, actually, running high frame rate vision models drains a robot's battery incredibly fast. So optimizing our code wasn't just about reducing latency, it was literally about keeping the robot alive long enough to finish the job.
The desired user flow is beautifully straightforward. Step 1, the user speaks a command. Step 2, the robot acknowledges and initiates a search. Step 3, our vision model actively scans and detects the item. And Step 4, the robot calculates a path and physically guides the user right to it. It sounds simple, but underneath those 4 steps lies just immense hidden complexity. Making them flow without interruption means the speech module, the vision module, and the navigation stack all have to operate as a single, unified brain.
Which brings us perfectly to phase 2, data and vision training. Let's get into my specific work on the machine learning and computer vision pipeline.
Any ML engineer will tell you that a model is only as good as its data, right? Before I wrote a single line of inference code, I spent a massive amount of time managing datasets and meticulously annotating training images using Roboflow. We had to ensure our dataset accounted for the crazy variety of angles, lighting conditions, and occlusions that the TIAGo would actually run into in a real physical space. Clean, accurately bounded data is the absolute foundation for everything that follows. For the model itself, I went with a YOLOv8 convolutional neural network. Now, why YOLOv8? Well, in robotics, latency is the enemy. The TIAGo is moving, its head is panning, the environment is dynamic. We literally cannot afford any lag. YOLOv8 is a state-of-the-art architecture optimized specifically for high-speed, real-time object detection. It gave us that perfect sweet spot: lightweight computational demands, but high mean average precision. That meant the robot could process the video feed fast enough to make instantaneous navigational decisions. To really optimize this network, I highly constrained its focus. We trained this YOLOv8 network to recognize just 4 distinct classes: plastic bottles, tennis balls, apples, and glasses. By locking the dataset down to these specific items, I was able to hyper-optimize the network's accuracy. It wasn't wildly guessing from a generic library of 10,000 objects. It was highly specialized to find exactly what a user might lose in our test environment. So we have a trained, highly accurate neural network, but a model sitting on a laptop is completely useless to a robot.
Let's transition to the third phase, custom ROS2 deployment.
To guarantee absolute stability and keep things industry standard, I architected the environment meticulously. The entire system is running on Ubuntu 22.04 LTS, utilizing ROS2 Humble Hawksbill. For the application layer, we used Python 3 and OpenCV. Now, managing dependencies in ROS can be, well, tricky. So I structured our requirements using apt for packages like ROS Humble CV Bridge and standard pip for our Ultralytics and NumPy libraries. This made sure we had 0 conflicts between the native ROS environment and our deep learning tools.
Because building the model is only half the battle. Packaging it up is where my deployment expertise really comes into play. I created a custom ROS2 package called TiCare Vision. This package is basically the container.
It takes our trained weights file and wraps it inside a ROS node. This node continuously subscribes to the camera feed, crunches every single frame through the YOLO network, and preps the output. We effectively turned a static Python script into a dynamic, integrated service running natively on the robot's brain.
And look, when you're working with expensive physical hardware, you don't just push code and hope for the best. I built testing redundancy right into the system architecture, using 2 distinct launch files. First, I wrote a sim launch file to test the node logic locally via a standard webcam. Once I verified the bounding boxes and inference speeds were solid in simulation, we seamlessly switched to the real launch file, pointing the node directly to the actual TIAGo hardware topic. This split approach, honestly, saved us countless hours of debugging. But isolated systems are great, yet seamless integration is what actually makes a robot autonomous. Let's look at how we made these separate nodes talk to each other flawlessly in Section 4, Seamless System Integration. The crucial bottleneck here is always managing network traffic. ROS2 relies on Data Distribution Services, or DDS, to pass messages around. When you're passing heavy visual confirmation data alongside navigation commands, standard middleware can sometimes drop packets. To prevent that, I explicitly configured our network backbone to use CycloneDDS. By setting that implementation variable across the entire workspace, I ensured communication between the vision, speech, and navigation modules was rock solid and genuinely real-time.
It's really like building a bridge. This exact architecture bridged our yellow detections right into the native navigation stack. We designed very strict publisher and subscriber topics. For instance, the comms module sends a head_up message, which physically tilts the robot's camera. Then it passes the target parameter, like object_bottle. Next, the nav node pings us with start_viz. Our vision node listens to all of this, acts as the state machine, and basically begins the hunt.
And then, you get the exact moment of success. When the YOLOv8 model detects that requested bottle with enough confidence, the vision node executes the ultimate handshake. It instantly broadcasts a string message, data, object detected, out across both the comms and nav topics simultaneously. In a fraction of a second, the robot translates what it literally sees into an actionable command, halting the search pattern and triggering the navigation stack to guide the user. It is incredibly satisfying to watch happen.
Of course, none of this happens in a vacuum. Complex robotics projects require intense collaboration. I definitely want to acknowledge the broader leadership of the TiCare project, Daniel Franco acting as CEO, Luis Gomez as CTO, and Marco Munoz handling design, with myself stepping in as the lead developer for the Vision module. Working in this professional hierarchy allowed us to lock down our API contracts super early. So, when it was time for me to integrate my deep learning models, the systems just aligned perfectly. The success of this project really proves that it's not just about writing code. It's about making hardware and AI work together seamlessly in the real world. Integrating deep learning with physical robotics is a complex challenge, but it is exactly what I specialize in. If you need custom computer vision models, YOLO deployments, or ROS integrations for your own projects, you can hire my services on Fiverr. Check out the link in the description to get started. The robotics revolution isn't coming. It's already here. The only question is, what will we build together next?